Hello, calculus students. Welcome to another online lesson. So we have learned the basics of antiderivatives or integrals last class, and today we're going to utilize those for something. Obviously, we understand that derivatives represent slopes, and there's lots that we can do with that. But now, what can we do with these integrals? So we're going to define and use the fundamental theorem of calculus today. Fundamental theorem. Sounds important. Quick review. Last class we talked about anti-differentiation. Differentiation is a verb for doing the derivative. The antiderivative is undoing the derivative. It is the opposite, so working backwards. We introduced some notation last time, including if we have a function f of x and we do the antiderivative or integral, we get big F of x. Another way to say that is using this symbol, which is an integral symbol. So we would say the integral of our function f of x in terms of x. That's what the dx means, or sometimes you'll hear with respect to x. Basically the same thing. So then we came up with a little rule last class. F of x equals ax to the n, which is our standard form for doing a derivative in seconds. Well, we can do an integral in seconds as well by taking that exponent, raising it by 1, and then dividing the coefficient by that exponent. Or it can also be written this way. Division rules work the same. So anti-differentiation is the same thing as integration, and the antiderivative is known as the integral. Last but not least, we need to remember that we're adding on a constant every time because there could always be a constant when we do a derivative that wouldn't show up with the integral. All right. Fundamental theorem of calculus. For a continuous function, meaning that it is connected, there's values continuously at all values of x, not just discrete like whole numbers or something like that. With an antiderivative of f of x, so we have a function whose antiderivative is f of x, we end up with this formula, which is the integral from a to b of f of x with respect to x. And that is the same thing as doing the antiderivative and plugging in b minus the antiderivative and plugging in a. So these are called like bounds or borders, upper and lower bounds or borders, and we plug those into our antiderivative. The fundamental theorem of calculus can be used to find the area under a curve, or graph may be better said, between the function and the x-axis, or y equals 0. Bordered by x equals a and x equals b. So what does all this mean? Let's say I have a quadratic function. So I've got a parabola, something like that. And I want to represent this on an x and y axes, something like that. Let's say I wanted to find the area of this region right here. So it's the area underneath the curve. Well, this right here, I'll use a different color, would be a specific x value. Let's call it b. Let's call this value right here a. This is my function right here. So I would do the integral of my function, we'll call it f of x, integral of f of x from a to b. And then again, we always write dx for with respect to x. And what does that mean? So I take the antiderivative of this function here, which becomes big F of x, and I plug in my higher value, which is b, minus the antiderivative of f of x, plugging in my lower value a. When I do that, it will give me this area right here, which I think is kind of amazing. So last year we knew how to find the area of circles, and because we can find the area of circles, we could find the area, underneath a piece of a circle. We could find the area of nice right angles like triangles and even non-right angles as long as they're straight edges using our rules such as law of cosines, law of sines for non-right triangles. But now we're suddenly able to find area under curves for all kinds of crazy functions, like parabolas, like I could do a sine function, which might look something like this, and I could find the area under that. Or even better yet, when I get to later on, we'll start putting two functions together, and I could maybe have a sine function going along, and then I could have an inverted parabola, and basically I've got like a Pac-Man ghost then that I could find the area of, something like that. So all kinds of cool shapes that we can now find areas of that we never could with basic geometry. We could maybe estimate at best, and so this is pretty important. Fundamental theorem of calculus. So to start with, we could do this first problem nice and easy, but I think I'm going to draw a picture first. So we've got a function y equals x. That's just a nice 45-degree angle going through the origin. So this would be my function, y equals x. I want to go from 0, which is my origin, to 2. Call that a 2 there. And my y is going to be equal to my x, so it'd be right there. And so we're basically looking for the area of this triangle right here, this shaded region that I've attempted to color in here. Now, could I do that without calculus? Of course I could do that without calculus. It's half of a square, a triangle, or 1/2 base times height. And my base is 2 here. My height is also 2. And so it's 1/2, 2 times 2. So 1/2 of 4. And so my area is 2 square units. Great. So you say, well, what do I need calculus for? Well, if we can show that it works for these simple problems, then we know that we're actually doing something that makes sense. So now let's try getting this same answer utilizing calculus. So we are going to do our integral from our lowest value, goes on the bottom, just like on a y-axis, to our highest value up there. And then we have our function, which is just x. We always write dx. And that integral would be equal to, well, we raise our exponent, so it becomes a 2. And then we divide it out front. So our raised exponent is a 2. Up front, we have a 1/2. Now, I haven't plugged in my values yet, and I want to still indicate that. So what we'll do is we'll put a little, it's like half of a bracket. I mean, I guess it's a full bracket, but we just put it at the end. We don't close it. Sometimes I've seen that, but usually it's just open here. And we still just put our borders on there, or our boundaries. So from 0 to 2. And what that shows is that I've done my integral, but I have not yet plugged in the values. So now I'm going to actually plug in these values and subtract. So I have 1/2 2 squared minus 1/2 0 squared. 0 squared is 0, and so this is gone. And 2 squared becomes 4, so I have 1/2 of 4, and 1/2 of 4 becomes 2 units squared. So I have confirmed that the calculus works here for a basic function like that. One thing some might be asking and saying, Mr. Peacock, you forgot your c's. Yes and no. See, the thing is, if I put a c here, which I certainly could have, but based on the fundamental theorem of calculus, if I had a c right here, I would also have a c right here. This whole thing is getting subtracted. So what happens to those c's regardless of what they are? Well, a positive c minus that c, they cancel out. So when you are using the fundamental theorem of calculus or finding area under a graph or a curve, you do not need to worry about your c's. You only need it when you're just doing a regular old integral or antiderivative without defined borders. They sometimes call that an indefinite integral. That's when you need your c. All right, so let's look at another example here. This one's the one that I kind of drew on the last screen. Now we have a beautiful parabola. Again, we can draw the picture. I don't have to draw the picture every time, but it's helpful for when we're starting. So put a quick scale on here. We're going again from 0 to 2. Parabola 1 squared becomes 1, but 2 squared becomes 4. So this part of the parabola is going to look like that. Again, it reflects over. So something along those lines is what my graph is going to look like. Again, just doing a quick sketch here. Going from 0 to 2, And so the 2 is my border, 0 is a border, the graph itself is a border, and the x-axis, I'm sorry, yeah, the x-axis, or y equals 0, is a border. And so I'm getting this. It's triangular in shape, but it has one curve to it. It's not circular. It's just got this crazy parabolic curve on the one side. Sort of looks like a sail of a sailboat. And I wish my lines were a little straighter, but that's what we got. So again, I need to write an integral of my function, which is x squared dx. I'm going from 0 to 2. Again, put your lowest value at the bottom, just like on the y-axis. And we can do our integral now. So our antiderivative, we raise our exponent up to 3. We divide by that new exponent or multiply its reciprocal. So I have 1/3 x cubed. And I'm going to show my boundary still go from 0 to 2. Now I'm going to plug those in. We start with the larger value, 1/3 2 cubed minus 1/3 0 cubed. You'll eventually get to the point where you really like when one of the values is 0, because the math often becomes nice and easy. So this one right away, 0 times anything is 0. Here we have 2 cubed, which is 8. 8 times 1/3. Again, minus the 0 that we had. That becomes 8/3 units squared. Question, do we always have to write a label there? Usually, if it's a real problem, they'll give you units, and then yes, you should write the units. It's an area, so it'd be square unit. Would IB take off if you didn't do it where there was no label? No, they wouldn't, but I would still be in the habit of thinking of this as area, so square units. So, awesome. The area there, 8/3 square units. Now, if we were to think of this as being a rectangle here, maybe I'll do that in the black. So this rectangle here, well, that would be a 4×2 rectangle, which would be an area of 8 square units. If we cut this diagonally, that would be half of that. And you can see this is a little bit less than half of that. And voila, 8/3 is a little bit less than half of my area of 8. My curve should probably be a little more drastic there, but that's the idea. Let's do one more. So here we've got one where I'm going from 1 to 3. So I write my integral, which goes, again, from 1 to 3 of the function x cubed minus 2x. Sometimes they'll put parentheses around this just to show that that is my entire function, and there's a dx there. I'm not sure they're required, but I'll go ahead and do that anyway here. My antiderivative, I raise my exponent up to a 4. I divide by the 4 as well, or multiply the reciprocal. For my second term, I raise the exponent up to a 2, and I divide by 2. Well, there was already a 2 there, so this 2 divided by that 2 become 1, but there was a minus sign still, so here we are. And you can always check your work. Doing your derivative of x squared does become 2x, and the minus sign's there. Great. So we plug in our 1 and our 3. Now I need to put this actually into my function. So first part is going to be 1/4 times 3 to the 4th power minus 3 squared. And that's just using my upper bound. Now I need to take my lower boundary, plug that in as well, subtracting all that, so I'm going to use parentheses. So in this time I have 1/4 times 1 to the 4th power minus 1 squared. Now it's time to simplify. I mean, literally, you could throw this all in your calculator at once right now, but let's see. So over here on the right, this becomes a 1. And we have another 1 here. And so you have 1/4 minus 1, which would be negative 3/4. But then there's this negative sign up here. So I'm going to bring all my work up here. And that would become a positive 3/4 on the right side there. On the left side, or the left part of this equation, which I'm underlining here, I've got 3 squared right here, which becomes 9. And I've got 3 to the 4th power, which becomes 81. And then I have a 1/4. So that's going to become 81/4 minus 9, also known as 36/4, plus my 3/4 that I had from all of this stuff here. Double checking my work. Yep, that looks right. Okay, so it's just time to simplify. 81 minus the 36 gives me 45/4 plus 3 more gives me 48/4, which reduces to 12 units squared. All right, fundamental theorem of calculus. One more problem. Diagram shows part of a graph. We have it here in factored form, 12x squared times the quantity 1 minus x. We know that must have been a cubic because if we distribute our 12x squared with the negative x, we would end up with an x cubed. So we see a piece of a cubic here. And we just want to know what our area is in the shaded region. So once again, one of our borders or boundaries is the x-axis. We have this value right here, which they did not give us, and we have the origin, which we know is 0. And we have our function. So the first thing we need to do is know what our other boundary is or our other border is. So we have to take our function and solve for our zeros or our x-intercepts or our roots or solutions or whatever you want to call them. Again, since it's factored, this is a wonderful problem. I take each of my factors, 12x squared, set that equal to 0. And I'll divide by 12, which is still x squared equals 0. Square root both sides, which is still x equals 0. And I already knew that answer. So that's not particularly interesting. My other factor is 1 minus x. Set that equal to 0. I can either move the x or the 1. I'm a fan of moving the things that are negative, so we'll move the x to the right side, which makes it positive, and x equals 1. Oh, great. So that's 1. Those are my two intercepts. Write down an integral which represents this. So my first integral is going to go from 0 to 1 of my function, which is 12x squared times 1 minus x. And that's to dx, I'm sorry. Now the thing here, that's a fine answer, you could leave it like that, but I don't like the fact that I have all of this stuff here because it kind of looks like product rule, and I don't know a product rule for integrals yet or anything like that. So I would recommend distributing this. So we could rewrite this whole thing as from 0 to 1 of 12x squared minus 12x cubed. And I got that again just by distributing here all dx. And if you'd like to, you could put that in parentheses to separate it from the dx. Now we're going to do our integral. Still haven't done that. Bring this up here. So I raise my exponent, so I have x to the third power. I divide the 3, so I have 12 now divided by 3, which gives me 4. For my other term, I raise the x up to the fourth power. Then I divide that 4 with the coefficient, which was a negative 12. Negative 12 divided by 4 gives me 3. And I still need to plug in my boundaries from 0 to 1. So we're going to go ahead and plug those in now. So I have 4, 1 cubed, minus 3 times 1 to the fourth power. I'm kind of out of room here, but I would have 4 times, parentheses, I guess, 4 times 0 to the third power minus 3 times 0 to the fourth power. And again, I'm sorry that's so hard to read, but we don't have to worry about it because 0 cubed times anything is 0. And then I have 0 to the fourth power times anything is 0. So this whole thing right here just becomes 0. And then these 1s are beautiful. So 1 cubed is 1. So 4 times 1 is 4. 1 to the fourth is 1. And negative 3 times 1 is negative 3. And this is all 0. So 4 minus 3 minus 0 gives me 1 unit squared. Or 1 square unit. Awesome. Great problem. Classic IB in that there's a lot going on, a lot you have to do. You have to show your pre-calc knowledge here by setting the factors equal to 0. You have to show that we can do our integrals and derivatives a lot more easily once we expand, sort of set up the problem. And yet, when it really comes down to it, the math was quite simple, and we get this beautiful whole number answer. Doesn't always happen, but that's very common on these IB test questions. All right, there are some problems we can look at on page 453, number 1, 3, and 4. And again, we have used the fundamental theorem of calculus to find area under graphs. Until next time.